So if you are with a company that produces something with model-based design, engineering, and manufacturing, then you're probably interested in using augmented reality to leverage that model-based data for the purposes of things like interactive product visualizations or training materials, offline training materials, or for things like field service in the field. So there's many different potential use cases. These are three I'm going to focus on here. So these three use cases represent a movement downstream from CAD data or the downstream to AR content. And in the case of interactive product visualization, it involves rendering to high fidelity. In interactive electronic technical manuals, or IETMs, you would like to leverage assembly sequences. And in field service documentation, you want to integrate with product database management or PLM systems. So this upstream, downstream can really be broken into two divides. That's between the model-based definition of CAD data and the digital content creation world. So the majority of AR content is part of the digital content creation world because it involves having to render things in real time. So what the dividing line between these involves some sort of translation between model-based data and digital content creation data. There's different softwares and different systems for each. And the translation is, in some cases, straightforward, in some cases not. Model-based data is almost exclusively parametric in nature. There is an equivalent of NURBS in the DCC world, but invariably, almost all AR content ends up becoming polygons. So this translation between parametric to polygons is critical. Certain things like assemblies, grouping, parts, coloring, these things correlate well, but other things like materials, like what is the density and what type of material you're using, doesn't correlate at all with how digital content is rendered, which uses shading and surface texturing. And things like assembly sequences or animations of how to assemble things don't always translate very well. And I'll say something about that later. So in the case of interactive AR product visualization, if we can export out of almost any CAD program to DCC formats, such as wavefront, or if we want to preserve colors that we may have colored our product, we can use something like STEP. And in the case of many of the tools to use photorealistic rendering, we can export those to native DCC formats. Now, these rendering tools are usually used to produce images or videos for product demonstration, etc. But they don't usually generate AR. But invariably, especially in interactive product visualization, some sort of manual intervention for surface shading or surface texturing is going to be required to get the visual fidelity that you want, primarily because the notions of the complexity of what makes something visually photorealistic in the model-based definition world doesn't translate. So as you can imagine, this pipeline doesn't work very well, doesn't scale very well, but it is often a necessity in proof of concepts. As the prior speaker was saying, it's not always that easy to get access to model-based data in its native format. But this does suggest that some other approach would be more ideal. Now, the exporting to DCC formats tends to be only as well, not particularly efficient. And that's because the model-based companies, it's not their primary business model to support the high-quality export of the data. So companies that focus on translation tools, Okino is an example, Spatial from Dassault. These companies focus on tools that accurately translate from native representations of CAD data into DCC formats. There are several ways you can do this. You can transfer your data to a cloud CMS and do the translation there. You can also access data in an enterprise CMS and translate it from there. Or you can even alternatively do the translation in the enterprise environment and then access that and use it for 3D or AR downstream. Now, one of the motivations for that, as the prior speaker also mentioned, has to do with IP concerns. These translation tools will decimate, which is converting parametric into polygons. They give you a lot of control over that, and they also allow you to generate things like levels of detail, low poly, high poly for different applications. And they can remove things that are parts that are not needed for optimization. But they can also do things like defeaturing, where they can remove chamfers, fillets, and holes. This can help to preserve IP, and other things can be introduced into the pipeline for those purposes. So in the context of that, for, let's say, interactive, electronic interactive training materials, this is a situation where we want to leverage, if we can, assembly sequences in the model-based definition world. These things, if we don't use them, we can always export to DCC, and then we can do these animations in a DCC environment. Obviously, again, that doesn't scale very well. But if you use a translation tool and you keep things in a native format, then you have a much higher possibility that you can get those assembly sequences translated into animations for use in your 3D or AR. And again, these typically assembly sequences in these model-based tools like CAD only generate things like images or video. And so they're not really designed from the beginning to create models or animations, which is, as they're called in DCC world. So in the context of let's say, field service documentation, this is an environment where we want to integrate with product database management or product lifecycle management. So when we're using translation, we can often use the native format for some of the mid-range products like Inventor or SolidWorks. They have PLM or PDM tools built in where they can generate things like interactive bill of materials and diagrams and schematics. So translation can retrieve that data and generate bill of materials for 3D AR applications. Some of the PLM systems will integrate multi-CAD formats from multiple CAD systems and generate formats such as the OpenJT format supported by Siemens, which is a good format to bring in for translation to 3D and AR. So I'm going a bit fast here, so I probably skipped some things, but I'm sure I'll get them here. So takeaways. The manual creation of AR, it doesn't scale very well. It may be necessary for proof of concepts, and it may be applicable when content is not going to be changing. But in an environment where you have real product lifecycle management, content is changing, and you have to manage your versions, and you have to be able to generate that content quickly and easily. So export to DCC formats is sort of a garbage in, garbage out. If you're going to export out for proof of concept projects or more static ones, you need to consider that you're going to have to go back to your model-based engineers who produce this and work with them with a process flow that makes sure that you preserve things like grouping, any available metadata in the data that they output. It's not as, you can't just simply go to a company and say, hey, give me your data, export it to any available package, and it will be useful. The reason for this is that it has to do with the translation between parametric to polygonal. If you have 100,000 screws, there are individual threads on each one of those screws. And if you are not careful, you end up with millions of polygons on the other end. Or if you're not careful in how you reduce that, then you end up with things that don't look like screws anymore. So it's really important to get at a minimum the model-based data saved out in a parametric format. So some of the formats, such as STEP, keep the parametric data in it so that downstream the persons who are generating the AR content can convert that, and they have some control over the polygon reduction. And if things are grouped, then different groupings can have different sort of decimation and polygon conversion applied to them, and this gives much better results. So this is definitely a must. So, and the final takeaway has to do with keeping as much of the upstream data in as possible. So the later you do the translation, the better. And this is why you would prefer to use a native format. And like I said, there are a number of companies who will say that they import these formats directly, but most likely they're using some form of translation on their side. And that gives them some control over level of detail and decimation. Also, pay attention to ideas such as change propagation. Not all of the solution providers are going to make it easy for you to simply make a change to your engineering data and have those changes propagated. This requires some symbolic assignments, and this goes back to how well your data is exported. If parts are symbolically assigned, then when the part has changed, then if you've put some downstream animation or labeling on it, then it's more likely that that will be able to smoothly and consistently move into the final AR product. And then, again, along that same theme, look for solutions that preserve assemblies. Assembly sequences are a powerful way that the model-based companies or environments generate training material, assembly material, and this is really an area where there hasn't been a great deal of success in translating this directly into interactive 3D or AR, but I think it's an area that's ripe for some increase there. All right, that's all I have to say. Thank you, and we'll take questions afterwards.